In chemistry, we're concerned about matter, but we're also concerned about the energy changes associated with matter. Chemical reactions sometimes involve heat being absorbed or released. That was one of the evidences of a chemical reaction. So we're going to talk about that. So chemical reactions can be exothermic. In science, we make a lot of use of prefixes and suffixes. This prefix exo reminds me of exit, right? Above the doors are red signs that say exit. What do you do when you exit? You go out, right? Exo means going out. Thermic has to do with heat, with energy. So exothermic means that energy is leaving. So when we talk about this, you have to put yourself in the position of the chemical reaction. So I am the chemical reaction, and heat is leaving me. That's exothermic. You can also have an endothermic. Endo reminds me of in, going into, endo, into. And so an endothermic reaction, I'm the reaction, that means energy is coming into me. It's coming in, okay? The amount of thermal energy that's emitted or absorbed can be quantified with a function called enthalpy. So there's a funny word, enthalpy. There's some subtle distinctions between enthalpy and heat and various things like that, and we're not going to get hung up on those small differences. So the enthalpy of reaction, we're going to abbreviate delta H reaction. You might wonder, well, why H instead of E? Just think of enthalpy as heat for now. Delta, that triangle is the Greek letter delta. That means change in. So it's the change in the amount of heat energy for the reaction. So the thing about heat and energy is it ends up being relative. You can measure the difference in energy, but it's hard to measure an absolute level of energy. So we just look at the difference. It's the amount of energy that flows either out or in when a reaction occurs at constant pressure. The sign. Okay, so we use a sign, positive or negative, to tell which direction the energy goes in. So here's an analogy that I find helpful. I think of the energy as being like money, and the reaction is like my wallet. So if money is coming into my wallet, maybe somebody just gave me some money, is that a positive thing or a negative thing? That's a positive thing. When energy comes into a system, a reaction, that's a positive thing. So delta H is positive. When energy leaves my wallet, no, not energy, money. When money leaves my wallet, that's negative. I don't like that. I want money to come in. So when energy leaves the system, delta H is negative. Here's some pictures. We can draw little energy diagrams. So on the y-axis, we have energy increasing as we go up. So an exothermic reaction, the reactants start out with more energy, and after the reaction occurs, the products have less energy. So this is me starting out with more money at the beginning, and I have lost money, and now I am poorer at the end. Money has gone out. Delta H is negative. The way we draw these diagrams, we also see that the change is going down, and down is usually negative. An endothermic reaction, the reactants start out at lower energy. Energy comes in, the change in energy is positive, and now the products have more energy at the end. So here's a chemical reaction, the combustion of natural gas. This is methane, which is the main component of natural gas, reacting with oxygen. This is a hydrocarbon. It just has carbon and hydrogen. We're combusting it, reacting it with oxygen, so the products are CO2 and water. Then it's just a matter of balancing the equation. Now we're adding something here. Delta H reaction. The enthalpy change for the reaction is negative. Does that mean that heat is coming in or going out of the reaction? It's going out. So think about a gas stove and you turn the burner on. This is the reaction that's occurring. Does that give off heat or absorb heat? It gives off heat, right? That's the whole point of the stove, is to heat stuff up. So this is telling us how much energy is given off. So 802.3 kilojoules are given off for 1 mole of methane that's burned. So the number here relates to molar amounts in this chemical equation. So 802.3 kilojoules given off for every 1 mole of this, for every 2 moles of that, for 1 mole of this produced, for 2 moles of that produced. So we could write that as a conversion factor. So we could say we've got 802.3 kilojoules per 1 mole methane. Or we could say that we get 2 moles of water for every 802.3 kilojoules that are given off.
You use the absolute value in your conversion factor?
Yeah, usually what we do, we definitely make a note of the sign, but a lot of times the question will have the direction specified in words rather than as a sign. You can definitely put the negative sign in here. It's not going to mess anything up. And I think we've got an example coming up. Here is an example of an endothermic reaction. So nitrogen and oxygen react to form nitrogen monoxide. Here, delta H is positive. That means the energy is going into the reaction. It's all a matter of perspective, right? So from my perspective, if I give money to Chris, to me that's negative because it's leaving my wallet. But to Chris, it's positive. So we have to put ourselves in the position of the reaction. This reaction has delta H plus. That means energy is coming into it. That's an endothermic reaction. Where does the energy come from? It comes from the surroundings. So the amount of heat absorbed or emitted depends, of course, on the amounts of reactants, right? If you burn a little bit of natural gas, you get a little bit of heat. You burn a lot of natural gas, you get a lot of heat. So we usually specify the delta H in combination with a chemical reaction, and we're going for that for the amounts of reactants as written. It's for the molar amount. So whatever the chemical reaction says, it's that many moles of reactants and products that would generate or absorb that much energy. Here's the combustion of propane. This is what you might have in your gas grill. This gives off 2,044 kilojoules of energy for every 1 mole of propane that's burned. And so this can form a conversion factor. So we can ask questions then like, well, if we burn 10 grams of this, how much energy is released? Here's an example with ammonia. Ammonia reacts with oxygen to form NO and H2O, and here's delta H. Is this an exothermic or endothermic reaction? exothermic. It's negative, the energy is leaving the system. Calculate the heat in joules associated with the complete reaction of 155 grams of ammonia. So I have 155 grams of ammonia, and I want to know how much heat. So I'm going to write the path out here. Grams of ammonia, and I need to convert to moles of ammonia. Because this number here, 906 kilojoules, that is the amount of energy from 4 moles of ammonia that's released. So I need to get to moles of ammonia, and then I can go directly to kilojoules of energy. I don't have to go to one of the products or anything else. It's just whatever term I have a mass for, I convert to moles, and then I can go directly to the energy. So 155 grams of ammonia, and I'm going to convert to moles of ammonia, and then kilojoules. I'm going to stick the units in the bottom so they cancel out. Those cancel. And I want grams of ammonia down here. Any questions? Now, we calculated the molar mass of ammonia in a previous slide, so I'm not going to do that again. It's just 17.03. 1 mole of ammonia, 17.03 grams. The kilojoules to moles of ammonia comes from the balanced chemical equation. Look, in front of ammonia it says 4. So 4 moles of ammonia. Kilojoules is the delta H that's given. It's probably less confusing if you leave the sign in there. So when I do this on my calculator, I've got 155 divided by 17.03 times negative 906 divided by 4. It's a big number. It's a big negative number. 2061.5 kilojoules. How many sig figs should that have? Should have 3. 206, that's the third one. This is in the tens place, so we need to be careful. Best to put this into scientific notation before we round it, so that we don't do something dumb. And, you know, we all do plenty of dumb things on our own. We don't need any more opportunities to do dumb stuff, right? I don't. The negative sign means that the energy is being released from the reaction. Sometimes on Mastering Chemistry, it will say something like, calculate the amount of heat in kilojoules that is given off. And then they probably want a positive number because they say it's given off. Sometimes we use words to indicate the direction, and sometimes you have to use the sign. And I know that's confusing, but there's nothing I can do about it. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? Producing kilojoules of heat. So if we're going to use negative signs, would that be negative or positive? It's negative because the heat is being given off from the reaction of the butane. Now, this chemical reaction looks funky, doesn't it? What's weird about it? It's got a fraction in it. It's okay. It's balanced. It's not the standard form for a balanced chemical equation, but it's what they gave us. And so, This number refers to these molar amounts. This is 6.5, 13 halves. It's okay. So we're asked to find the mass of butane. Well, you probably don't know what the formula for butane is because I haven't taught you that. I'm not going to. Could we eliminate the other things and figure out which one it is? Yeah, because this is oxygen, that's carbon dioxide, this is water, therefore, this guy must be the butane, right? So we want to know how many grams of that, and we're producing this much heat. So this is the number I'm going to start with. 1.5 times 10 to the third kilojoules.
Just work backwards to find the grams?
Yeah, I'm just going to do a very similar calculation to the previous one, but it's backwards, starting with kilojoules and going to grams instead of starting with grams and going to kilojoules. So now you kind of have to decide, am I going to use the negative signs or not? What do you guys want to do? Drop them? Okay, so if we're going to drop the negative signs, then you have to always drop them. Otherwise, you're going to end up with negative mass, and hopefully you recognize that that only happens in science fiction novels. So this much energy being released, we just understand that that's really a negative number. I'm going from kilojoules of energy to moles of butane. And then it's asking me for grams of butane. And I stick my units in here. And this will be kilojoules down here. The relationship between kilojoules and moles comes from the equation. So this is saying 2,658 kilojoules given off for every 4 moles of butane. 2,658. Grams per mole, that's the molar mass of butane. So we need to calculate that. 4 times 12.01 plus 10 times 1.008. And 10 seems like a big number because most of the things we do are smaller, but it's okay. $58.12. 1 mole of butane weighs 58.12 grams. So I've got 1.5 EE3 times 4 divided by 2,658 times 58.12. And this should have 2 significant figures. I'm getting 131.196 blah, blah, blah grams. But I need to round to 2 sig figs. We don't want to round this off to 13 because it's 131. Put it in scientific notation first. And then you can round it off safely without having to do too much thinking. So if you needed to generate 1.5 times 10 to the third kilojoules of heat, you would need to burn 130 grams of butane. Any questions? And then it's asking what mass of carbon dioxide would be produced when that happens. Well, there's two ways to calculate that are obvious to me. We could just take this and find the mass of CO2 instead, or we could take this mass and find the mass of CO2. but since we're dealing with the energy here, let's do the energy way. So it's going to be real similar. 1.5 times 10 to the third kilojoules. I'm going to go to moles of CO2. This is going to be 2658 kilojoules. CO2 also has the number 4 in front of it. And then I need to find the mass. So I want moles of CO2 down here and grams of CO2 up there. So I have to calculate the molar mass, 1 carbon and 2 oxygens. Happens, that's a really bad zero. 44.01. So 1.5 times 10 to the third times 4 divided by 2658 times 44.01 equals, again, this should have 2 significant figures. I'm getting on my calculator 99.345. So that would round to 99 grams of CO2. So if I burn 130 grams of butane, I'm going to get this much energy released, and I'm going to produce 99 grams of carbon dioxide. Any questions? Okay, so this is a little blurb about the sign. Often in the homework, the absolute value of Q, we haven't talked about Q, have we? Q equals heat. The absolute value is requested. Words are used to convey the signs. It's saying heat absorbed, heat given off, and so a lot of times we use the absolute value and just ignore the negative signs. But just be aware that they're there and they do have meaning. We used Bunsen burners in lab the other day. And they have a little thing that allows you to adjust the amount of oxygen, right? Oh, I'm not going to look at all those words. You can read the words. Let's look at the pictures. So this is what you get if your Bunsen burner is not getting enough air. It looks like a candle. This is not efficient burning of the natural gas. It's giving off a lot of light, which might be good if the power was out and we needed the Bunsen burners for light, but it's not giving out the maximum amount of heat because there's just not enough oxygen present. If we increase the amount of oxygen, we see a flame that's getting better. It's getting smaller and bluer. The problem with this flame, what happens when you burn lots of candles in your house? They're smoky, right? And after a while you get soot depositing on things near the candles, and it's messy. And if you use this sort of a flame to heat something in the lab, what you're going to find is the bottom of your container gets black with soot. And we generally don't want that. As we increase the amount of oxygen, we have less carbon that goes unreacted. It's more efficient. We just get carbon dioxide and water produced, and we don't get carbon deposited all over the place. So this is your ideal flame. You have a nice inner blue cone and an outer blue cone. And the hottest part is right here at the top of the inner blue cone. This is what happens if you give the flame too much air. It's a little hard to do on our cheapy Bunsen burners, but we did see it with somebody the other day. And here it looks like the flame is floating, right? This one's getting too much air, and the bad thing about that is it's going to be unstable. And if you've got a little breeze or an air current, it might blow out. And then you've got just natural gas coming into the air, which, that's not very safe. And there's the end of chapter 8.